Okay, well, welcome everybody. Good evening, and welcome to the Cheng Shun Digital Hub at Jesus College. I'm Professor Sanadra Chabot, Principal of Jesus College, and I'm delighted to welcome you to tonight's 2025 Cheng Shun Digital Hub Lecture. So our annual Digital Hub Lecture celebrates the latest cutting-edge research being undertaken by Jesus College Fellows in scientific and technological areas of research. The annual lecture is organised collaboratively between the college's alumni and the Cheng Shun Digital Hub events programme. So thanks to Peter and to Janina for supporting us on that. To give our 2025 lecture, I'm delighted to welcome Dr. Oiwi Parker Jones. Oiwi is a Hugh Price Fellow in Computer Science at Jesus College and a Principal Investigator at the Oxford Robotics Institute, where he leads the Parker Jones Neural Processing Lab. In his talk, he will discuss the promises and challenges of brain-computer interfaces, BCIs, that can restore communication to profoundly paralysed patients. His team weaves together the research threads of computer science, neuroscience, language and speech, with the aim of creating safe and effective brain-computer interfaces that can help paralysed patients to communicate when they are unable to speak or gesture effectively themselves. Utilising the power of modern machine learning is key to the success of speech BCIs. In this lecture, Oiwi will describe his lab's initial research breakthroughs using large-scale machine learning methods and the challenges that lie ahead in his quest to help paralysed patients to communicate again. It is my pleasure to now hand over to Oiwi to give the 2025 Cheng Shun Digital Hub Lecture. Oiwi, welcome.
Thank you, Nigel. Thank you for having me in Jesus, first of all. Thank you for having me tonight. Thanks to everyone for coming. I possibly have slightly too many slides, so if I jump over a few things. And we did something very foolish at the last minute. We switched from Keynote to PowerPoint, so if I look flustered, it may be that there was a conversion error. That's my story. Right, so let's get into it. So I'm going to start by saying who I am. I'm Oiwi. It sounds like saying the letters O-E-V. And I have to tell you, it's a Hawaiian name for this joke to work. The joke is, the research group is called Pineapple. Thank you very much. We work at the intersection of machine learning, neuroscience, and engineering, and we're primarily working on brain-computer interfaces, as Nigel says, primarily to restore speech to paralyzed patients. So the group is at the moment myself, a software engineer, a postdoc, some other postdoc associates, some DPhil students, some of whom are here today, a visiting master's student, some incoming PhD students, some master's students, one undergraduate, and a bunch of friends. So the main problem we're working on in the group is called brain to text, and it's very much like speech recognition. So if you think about speech recognition as a continuous input going in, so audio over time, and then output is a transcript, we're working with a continuous input, which is brain signals, and at the output we also want transcripts. So it's meant to be a technology where if you're paralyzed, you could think what you want to say, and the machine would be able to translate that into a transcript that could then be voiced if you want. Here's an example of what it looks like. So this is data from a surgical patient. So you can see the brain. The blue dots are electrodes on the surface of the brain. And on the right of it is a matrix showing time, and for every time point, a probability distribution. So how likely each of the possible letters are. And over time, we're building up a map of how likely every letter is over time, and then we find a path through that. That's a very similar technique to speech recognition. So here's what it looks like.
To which this nation has always been committed, and to which we are committed today.
This isn't our work. I think I might have got this from you, actually, Nigel. Yeah. Yeah. So you can see this is the kind of problem we're trying to solve, primarily for text, but also secondarily for control signals to robots. which we'll touch on very briefly today. Why do we want to do this? Primarily, it's for paralyzed patients who can't speak. So imagine people like Stephen Hawking. The worst case scenarios are people with what's called locked-in syndrome. So imagine being a brain in a vat, effectively. So you can't move, you can't communicate, but you're fully conscious. And it's not a high incidence, but the suffering is very high. And we're at a moment now where the technology is just about able to help these people. So it's a very exciting time. It raises ethical questions, which I'll touch on at the end as well, that we're thinking about. But let's talk about the science first. So over the past few years, since 2021, we've seen a rapid progression of advances in this field using surgical implants. So 2021 was the first demonstration in a paralyzed patient of this technology working. And then rapidly, we've seen a few basically incremental improvements that have gotten us to where we are today. Let me show you what it looks like. So this is basically state of the art. There's a woman here with electrodes implanted into her brain. She's looking at a screen. She's not fully paralyzed, but she has difficulty speaking, so she can't speak in a way that she can make herself understood. And so there's some text on the screen. There's a big square. When that square changes color, that's her cue to try to produce the speech. And you'll see in real time the algorithm transcribe and then voice. And I'll show you a few examples. There's an error, which I think is a little bit funny.
I don't have a lot of time to do it.
So that's perfect.
When I'm up here.
Exactly right. Here's the error.
I enjoy the bombing.
At which point, the airline people take her into a back room and take away her machine. But it's pretty good, right? So this is possible right now if you're allowed to implant electrodes into someone's brain. The main difficulty with this technology, in my opinion, is that brain surgery is a very high bar to ask. So there are two main sensor types that are available right now. There's a lot of work on alternatives, but these are the ones that are available. There's electroencephalography. Sorry, warning. You do a craniotomy and you slap a bunch of electrodes directly onto the surface of the brain. Or there are microelectrode arrays, where you have these little beds of basically nails that you then stick into the brain. Both of these are pretty nasty. I think my partner works in a surgical team and she sees people having brain surgery every week, and you basically don't want to have the blood-brain barrier passed unless you're very, very desperate. So if we could provide an alternative that didn't require any of the surgery, that would be very good. And yeah, basically that's the motivation. The other point is that actually surgical data is very hard to scale. So this data is really dear. Getting a few hours is a pretty big coup. Dozens of hours have pushed the state of the art. It's hard to imagine scaling that to hundreds or thousands or tens of thousands of hours, but we can do that non-invasively. So that's effectively our working hypothesis. We know that non-invasive data is not as good in the sense that the signal-to-noise ratio is lower, but we think that with enough data and with the right machine learning methods, we'll be able to compete with brain-computer interfaces. That's our gambit. That's what we're trying to test. So here's kind of a schematic of what we're doing. So here's some person, and you can imagine some non-invasive sensors outside of the head in this case. And then the plot is showing on the x-axis, as you scale the amount of data, as you have more data, the y-axis is showing performance, so higher is better. The red zone is kind of where most data sets lie. The green is where you get to the big data regime. And this is a proof of concept showing two models. So the dashed line is chance. Dark blue line is showing a deep learning model, and the light blue line is a control linear decoder. And the linear decoder basically shows that having more data doesn't help you. You need deep learning. So you need the right kinds of models and the data, basically. So basically, you can think about what we're doing in the group in two ways. One, we're trying to extend that x-axis as far to the right as possible. Scale up that data. Two, increase the slope. So create methods where we're improving faster so that you can do better with less data. And by combining those two strategies, we hope that we can get to a point where we're producing something useful that people could actually use. Our skill set involves actually data collection. So we do have people in the group collecting data, and we're collecting at a very large scale. And I'll say more about the data that we've just released and that we're using to host a competition. We develop machine learning methods, and we look at the foundational neurobiology. So we care about what the signals are, the full stack. We want to understand how the brain does, for instance, inner speech. How is inner speech represented in the brain? And by understanding it, be able to build tools that will be able to translate that into text or speech for people who are paralyzed. So today, the title of the talk is The Promises and Challenges of Brain-Computer Interfaces. We're really going to focus on here non-invasive BCIs and particularly speech. But I'll touch very briefly on some BCIs for robots. But like, if you blink, you might miss it. Exactly. So today, we'll talk about, first of all, scaling existing data sets, then scaling new data, so data that we've created, and the competition. We'll briefly note ways of increasing the data set by using synthetic data and also multimodal data. So how much can we use data from other domains, like speech or images, to help us with brain decoding? And we'll also talk finally about a recent paper that was led by one of my DPhil students, Dohan, in the audience, which has made some significant progress towards building a full brain detect system non-invasively. We're definitely not there yet, but we've moved things forward in a significant way, and that's very exciting. And finally, we'll talk about outlooks and opportunities, and if anyone's looking for like a master's project or DPhil, come talk to me afterwards. Basically advertising. Cool, so scaling existing data. Maybe you don't know what neurodata looks like. fMRI, this is an fMRI scanner. This is the one we have in Oxford. It produces sort of these 3D volumetric maps of the brain. You can think of these volumes as being 4-dimensional, so like a volume for every sample in time. And exactly, so that's kind of what fMRI looks like. We're mainly going to be talking today about electrophysiology, so EEG and MEG. And there are two types of MEG. There's old-fashioned squid MEG, which is mainly what we work on. So that thing on the head is called a superconducting quantum interference device, a squid. And the alternative is the OPM, which is the optically pumped magnetometer. So it's basically a room temperature meg, and that's kind of cheap and portable, but you still need a magnetically shielded room. The data look like kind of like audio. If you see audio traces, you have maybe one audio trace for each channel. Here we have channels for every sensor that's outside of the brain. And you can imagine then annotating your data. So saying this is the period in time in which someone was thinking hello, world. You then put your model there. You then predict what you want to predict. Here's an example model that we've used in the past. Just to give you a quick, just to basically describe my terms, we're talking about decoding here. This is an overloaded term in machine learning, but we're using the computational neuroscience sense of decoding. And that's where you think of encoding and decoding in the sense of encoding goes from some stimulus to a brain signal, and decoding goes from a brain signal back to a stimulus. So for instance, you might try to decode what pictures somebody saw from their brain data. You might try to, so here's reconstructed images from brain data, fMRI. You might try to reconstruct what people heard, and you might try to predict inner speech. Here's an example of reconstructing or decoding audio from the brain. I think some of you have seen this before. So there's the original Pink Floyd song on the left, and the reconstructed. I'll play a little bit of each. Oh, I think that's just the reconstructed. Well, if you know the original, it's kind of similar, but like I think it's on brand, being kind of trippy. So it works in this genre. But yeah, that is audio reconstructed directly from brain signals. Oh, there's the original.
All in all was just a break in the wall.
Classic. Cool. So talking about scale, even big surgical data is small, so big data is tens of hours. If you compare that to speech recognition, state-of-the-art speech recognition is at least in the hundreds of thousands of hours. So that's kind of like, I don't know if I have my numbers right, the cost of a cup of coffee versus the cost of Tesla. So we're trying to scale up from a cup of coffee. I mean, that's a really big gulf to get past. This is kind of where the current data sets sit, that tiny dot on the left for non-invasive. We are very close to being here right now, and in the next few years, we hope to be here. And I point that out just to kind of make the point that it's kind of a qualitative change. Sometimes bigger just sounds like it's bigger, but this is going to be a big, the size of the data makes a really big difference. So first of all, how do we extend the data set? Well, the first idea is to take all the existing data sets and collect them, put them together. The problem is that combining data sets and then into one pool for brain data doesn't tend to work. So if you just do it naively, you get worse results than if you were just to use one data set. But we've been able to get past that in the following way. So I'll describe what we've done here. And this paper is called The Brain's Bitter Lesson. It's an homage to our patron saint in the lab, Rich Sutton, who is famous for talking about the bitter lesson in machine learning. And the bitter lesson is that no matter how fancy your algorithms are, in the end, more data and more compute always win. So that's the bitter lesson. We have his portrait in the lab if you guys come to visit, and we bring him offerings often of bitter things, like bitter chocolate, bitter. Yep, and anything bitter you can bring, you can leave at the shrine. Cool. So here's how we did it in this case. So first of all, I'm going to remind you how supervised and unsupervised learning works. So here's an example of a supervised scenario. So the D is your data set. So it's a set of pairs of X's and Y's. So every X comes with a Y, and you have a number of them. Unsupervised is where you just have an X. So what are the X's and Y's? The X's could be like pictures, and the Y's could be labels, like a picture of a dog. So for instance, here, the supervised data set are pictures of cats and dogs, and the labels are cat or dog. And the unsupervised data set would just be the pictures. So there's no extra information telling you if it's a cat or a dog. So you can turn unsupervised data into a kind of supervised data via pretext learning. And that works in the following way. So let's say you change the image in some way that you control. So maybe you rotate the image. Your label can then be the degrees to which you rotated it. So here, 0 degrees, 20 degrees, 120 degrees. And then you can treat that label data set as a label data set and train on it. We've done something similar with brain data, basically. So here we took a big unlabeled MEG data set. We applied some transformations, T. There's a set of transformations. And we basically trained a kind of backbone model. Once that model was trained, we then used it for a downstream task. So we fine-tuned it. So how do you transform brain data? So here's one of our subjects in the scanner. That's me. And here's what the sensors look like around the head. We're measuring magnetic fields, magnetic flux. So in a cortical column, if enough neurons fire together, they create electrical potential, and every electrical potential has a magnetic corresponding field. We're measuring the magnetic field. So it's the same thing underlyingly. So we're measuring directly neural firing at the population level. And the data, as I said, is kind of this time and channels situation. Okay, so you can rotate pictures. What can you do with brain data? So a few things that we tried that worked is to basically change the amplitude of the different channels. So we know how much, so you can imagine these dials are turning. We turn it up, and we can use how much we turn the dials as our label. We can also change the phase, so we can effectively move them forward and backward along the x dimension. And we can also separate the data into different frequency bands. And what does that mean? That means that we can take any signal and decompose it into power at different frequencies. And then we can, for instance, drop some frequency band and reconstruct the data, and then try to predict which frequency band did we drop. So that gives us 3 pretext tasks. So we treat them all as classification tasks by quantizing. So instead of treating the changing of the amplitude, for instance, as continuous, we treat it as steps. That gives us some losses we can use. And then because they're measuring complementary properties of the mixed signal, we can throw them into one big loss at the end. And that's our self-supervised learning loss. Okay, that's the math. Here's some pictures. This is what the model looks like. This diagram is showing you the inputs. This is where the brain data goes in. There's an encoder block, so we need different data sets have different numbers of sensors. So we have some part of the network that maps from different numbers of sensors into a shared number of representations. We then have a pretty standard stack that we stole from speech processing. So this is the sound stream model. So it's kind of state-of-the-art way of encoding audio, but we've tweaked it a bit. We also have here subject-specific information, so we tell it which subject it's been given at any given time. And these are effectively like a kind of word-to-vec style approach. And then for our self-supervised learning, we have those 3 tasks. So that's being projected here into each of those heads. Then we have that loss at the end. And then we have our downstream task. So here we're looking at 2 tasks that I'll talk about later. and we have a loss for that as well. So those are all the parts of the model. The downstream tasks we're doing are speech detection. So on the right, you can see on different tiers an audio trace, a spectrogram, another representation of audio, and on the bottom, the corresponding brain signals that we're recording. So all the channels are just overlapping right there in what's called a butterfly plot. We can annotate this and say different parts of this correspond to speech or non-speech. So there's actually text at the very top. This is a subject listening to Sherlock Holmes. So the text is, A Study in Scarlet, pause, by Sir Arthur Conan Doyle. And so we know where in the audio data there is speech and where there is not speech, and we just carry that over into the brain data. So we know where in the brain data there is speech and not speech. And we also look at phoneme classification. So phonemes are effectively the letters that build up speech and language. And we can also say where those are. So this is the this is this, So we know where all this information is in our brain data. So the downstream task is to learn to predict for any given brain data, is it speech, is it not speech? For any given brain data, is it an example of or s or some other sound? And basically, in a nutshell, this is what the study shows, is that as we scale up data, again, in the x dimensions, so going from left to right for each of these plots, as you increase the amount of data, performance goes up. And this is over, this is a log scale, so 10 to the 0, 10 to the 1, 10 to the 2. So this is into the hundreds of hours of data. And we're showing that as you continue to increase, performance is increasing over 2 different data sets. Another way that we've used, I'm just briefly going to mention, to improve existing data is to use what's called domain shift. So the question is, what if we explicitly adapt the data model to remove data set specific information? So there are a few ways you can do this. One is like style transfer. Oh, I got the wrong slide. There we go. This is the one I was expecting. So we can imagine style transfer. So the picture on the bottom right shows you a picture and then a second picture. And the second picture is giving you the style, and then it's giving you the first picture in the style of the second picture. So you can effectively take some domain and shift it to another domain. And you can imagine data sets are your domain. So you can say data from data set 1, I want in the style of data set 2. So you can change the actual data that you're working on. So that's style transfer. So you can adapt the input space to harmonize your data. A second approach is to effectively do that inside the model. And I'll show you how that works. That's called domain adaptation. So we've done this and got some signal, and that's why I'm showing it to you. So basically, we're looking at another model diagram here. There are 2 parts to it that I've labeled on the left, W encoder and WSSL, so self-supervised learning. And on the very bottom, you can see it's minimizing effectively the loss for those 2 parts of the model. So basically, you're trying to say, be better at the tasks we care about for both the encoder and for the self-supervised learning part of the model. And we want to do that again for the task part of the model. So basically, we're training the model. We're saying, be good at the tasks. That's all kind of as you should expect for machine learning. We then train this domain classifier. So this here is trying to predict which data set does this specific data come from. Is this from scanner, the Oxford scanner? Is it from the London scanner? Is it from the Cambridge scanner? Is it from another scanner? And we're learning another part of the model to predict that. Once we've done all of that, we can do the really tricky part, where we can say, we want to maximize. So we're trying to tell the model to forget, this part of the model, to forget which data set the data comes from. So we're able to predict what data set it comes from, and rather than try to minimize into the encoder, we're maximizing. So we're telling the model, forget what you know about which data set, just be good at the task. Yeah. Cool, so that's kind of how domain adaptation works. We've done that, we've used that to extend a Facebook model where they've shown here are 2 different data sets. As they increase the amount of data, performance is increasing for each of those 2 data sets. They weren't able to combine the 2 data sets. They've put them side by side in a very suggestive way to look like they're continuing, but it's not. It's 2 separate data sets. Taking their model and using this method, we were able to improve. And one way you can see that we've improved it is if you look at a representation of the inside of the model. So this is a projection from some representation to a low dimensional space so we can make sense of it. And on the left is the original data from 2 different data sets. And you can see the green and the blue are separated. And after we've gone through this process, they've all been bunched together. So the point is that this model can still do the task, but inside the model, it's forgotten which which scanner it's come from. Yeah. So you can easily discriminate on the left, but on the right, you'd be hard-pressed to find a line that passes through those two different data sets. Cool. So that's some of the work we've been doing on trying to make other people's data useful for us. The second part of the talk, I want to talk about the data that we've been collecting and what we're excited about in that context. So we've just released a data set, but we're still expanding it. We're aiming for hundreds of hours. We're releasing 50 hours. We're actually aiming for thousands of hours. And we're going to host a series of competitions every year, we hope, for the community to become involved. So we're sharing the data, and we're asking people we're basically gamifying the problem, and we're crowdsourcing it to say, help us solve this problem. Here's a lot of data. Here's a very simple way to use it. And here are some tasks, and let's play a game and see how well we can do it. So this is the first big data release. We're calling it LibreBrain. This is a play on other data sets in machine learning like LibreSpeech. And it goes back to the LibreVox project, an open project where people voluntarily read books, audiobooks, full audiobooks, wonderful recordings, and post them freely on this website. So all of our audio data comes from the LibreVox project. So we're building on top of that. And we're releasing our data in the spirit of it. So our data is also free and open. So the motivation for the data set, here we're showing the size of previous data sets schematically as these circles. So this is per subject, and this is basically the scale difference of our data set compared to previous data sets. At a glance, it's just over 50 hours. It's split into a standard train, validation, and test. There's also a competition holdout, which we haven't released in order to avoid data leakage. Here are some statistics per split. You can see how many words and phonemes and minutes and hours. So it's basically still 50 hours of data for training and just over 52 hours for the full data set that we're releasing. This was acquired here in Oxford at OBO using 306 sensors across the brain. And it's been downsampled to 250 hertz. So a sample every 4 milliseconds. And that lets us resolve signals into what's called the high gamma range, which is kind of the highest range of brain oscillations that neuroscientists are currently interested in. We've also released the Pineapple library. So I don't know if you can see the picture on the top right. This is something I found, a frozen pineapple. This is the frozen pineapple library, the one that we're not updating for the competition, so this will be persistent over time. If you want to download it, you just go to your terminal and you type pip install pineapple. If you want to download the dataset, you go into Python and you write from pineapple.datasets import LibreBrain speech. And then you just instantiate the object, and the dataset will load to whatever directory you give it. And if you want to integrate this into PyTorch, it works just like any other data loader from Torch Vision or anything else. So it's meant to be very easily used by the machine learning community. And yeah, you can also just download the data from Hugging Face if you want. At the same time, we're releasing public leaderboards. So this is the part where we gamify the problem. So this is over time. You can see how people progress on the task. And the two tasks we're using are, again, speech detection and phoneme classification. So these are examples from our data showing basically predicting where is speech and where is not speech and which phoneme is happening at any given time. We also used word classification. And these are the results. Trust me, they're good. Better than chance, effectively. So we're showing to validate that the data are good. We've done some simple models. Actually, the idea was not to make very good models. We wanted the directive I gave the team was a simple model that anyone looks at and says, ooh, it works, but I can do better. And these plots are showing that for each of the tasks, as you scale up the data, you improve performance. So this is confirming what we've seen before, that as you increase data, performance increases as well. On the far right, we're comparing our data set to the previous best data set, which is the yellow, and we're seeing that the quality of our data seems to be better. So for the same amount of data, in any given amount of data, the same model decodes better for our data set than for other data sets. And part of the reason our data set is good is we've done a lot of sanity checks, so we can say which sensors are driving things, we can look at the data, we look at the confusion matrix for the phoneme classification, and things tend to cluster in useful ways, and we looked at the words, and everything makes sense. The funniest thing we've done, I'm just going to show you one example, to quality control is what we call the henna test. So here's again a subject in the scanner. And one of the things I should tell you is before we go into the scanner, we put electrodes onto the subject's head and face. So first of all, we have electrodes to measure blinking and any kind of mouth movement to make sure they're not talking when they shouldn't be. And we also put sensors to basically track inside the scanner if the head moves at all. Those are called HPI coils. And this is a diagram for our study of where we put all of the electrodes and coils. It's hard to see in this picture, but this subject volunteered to have henna drawn on his face. And I should point out that henna does not go away for a number of weeks. So there might be a resemblance, I guess, if you see the person. But if I put it that way, I can say this idiot walked around for weeks with henna on his head for science. And you can see there's henna drawn here, and it corresponds to these on the head. We did this so that we could test 3 conditions. One was the freehand placement of those coils, which is the standard method. The second was using the henna from scan to scan, day to day, putting the coils exactly in the middle of the X. And the third condition was intentionally putting the coils away from the middle of the X to see what happens if we deliberately try to increase the variance. And the result is nothing. It didn't matter. But I show you this to show you the amount of work we put in, representative of how much work we put in to make sure our data set was very good. And I could show you many other things, but I definitely won't. Cool. As I say, we're launching a competition, 2025 Pineapple competition. We've got at least $10,000 in prizes. We're hoping we might raise a little bit more. Yeah, feel free to participate. We're going to have a Discord server. We're hoping to have regular blog posts and we want to create a community around this problem. At the moment, there's not a lot of machine learners who work in this area, and we're trying to create the community that we want to be part of. So join us. We're fun, we're friendly, and let's do something good for science. This is the team who did the competition. It was a collaboration between our group and some industry and some other universities. And you have 4 chances to win. So there are the 2 tasks, but there are also 2 tracks. So the standard track is where you can only train on our data set, the LibreBrain data set, and then evaluate on the holdout data set. And that's to keep the bar small for people who don't have a lot of computing power. The extended track, you can train on any data you want. And the reason to have that is we want to see how people can scale up. But we know that that's probably going to be, you can imagine that would be pushed by maybe big companies or people who have unequal access to compute. So we've separated that to keep, to give lots of prizes and to increase participation. And here's a timeline. We're hoping to start the 1st of June. We're waiting to hear from NeurosCience, where we submitted this on the 26th. Actually, they were supposed to tell us last week, and I was going to come here and tell you that it was on. I don't know if it's on, but hopefully it's on. If it's not on, we'll find some other way to do this competition this year. But the basic timeline would be 2 months to do the speech detection, 2 months to do phoneme classification. Then we'll finish with enough time for anyone who wins to apply for a visa to go to the US if you should choose to go to the US, because NeurosCience will be in San Diego in December. And if you want updates, there's a website. Here's the website. Or if you're bold, you can follow me on X. Yeah. Peter made a good joke that I shouldn't have crossed out Twitter. I should have X'd out the Twitter. Cool. So very briefly, I'm going to interlude and talk about scaling synthetic data and multimodal data. I'm not going to say much, just to say that we're also working on this. So synthetic data is data that you generate from a model. Sometimes I'm asked, why not just train it entirely on synthetic data? In our experience, synthetic data can improve if you add it to real data, but if you add too much synthetic data, you do worse. So in our results so far, about 10% of the real, if you add 10% synthetic data to your real data, that seems to be optimal. But if you add, say, 15%, you go down. And you can imagine if your generative model, if your synthetic data isn't perfect, that you're starting to train on bad data for the real world. So that's basically why. So it helps, but it's not a panacea. And multimodal data is the idea of, we said before, of training on data from different domains. So there are many ways to do synthetic data. We're exploring a number of them. And for multimodal models, we've done some initial work working with colleagues in China. And this is the new GPT model. It's taking different kinds of inputs. So there's audio data, there's text, and there's brain data that go directly into it. And then outside, a similar kind of thing. Effectively, you can treat this as a chatbot, where you can, as part of your chat, put in brain data. So there's a way to code brain data. So you can say, here we're telling the system is being told, you are a helpful assistant named new GPT. You can understand and produce neural signals, and you can interact with speech and text modalities. And then the user says, please convert the following EEG input to text, and then here's the input, and then here's the code for the brain data, and the output is the text that the model predicts. So incomplete page before him, his pen flickered. So this is a kind of chatbot version of what we're working on. You can extend this. So this is hypothetical. This hasn't been built yet. But you can imagine adding more modalities. So vision or any modality that you can think of. And also we're thinking of using this to extend into robots. So that's my robot pitch. Cool. So now we're on to the part where I tell you about unlocking non-invasive brain-to-text. The first thing I should tell you is that a number of people have tried to do this in the past, but the results have been pretty weak. And so we use a metric in brain-to-text, which is the same as in speech-to-text, which is the word error rate. And word error rates range from 0 to, well, actually infinity. They're unbounded. But 100% is basically telling you nothing. So a word error rate of 100 is basically gibberish. So effectively, all prior work is at 100%. And there are other metrics that people have been using that are maybe easier to do well on, but the results have been pretty, maybe underwhelming. So we wanted to push forward on all of the metrics. But first to say, there was a kind of false alarm. So a few years ago at NeurIPS, there was a paper on a model called D-Wave, which got a lot of attention because it was claiming to do pretty well, I think around 80% word error rate. Yeah. And people were very excited about that. It turns out they had a bug in their code. And the reason is very, very understandable and kind of, so they had taken somebody else's code base and reused it, and the bug was in someone else's code base. So let that be a lesson to you. Be careful whenever you just take someone else's code. So this was shown to basically be at chance level. It's not actually producing anything useful in word error rate. There have been a succession of other things taking big swings at this as well, including the new GPT paper, but for word error rates, they're all doing at chance again. Basically, other studies have been trying to make progress by looking at easier tasks, more fundamental tasks like we've talked about earlier, so speech detection, phoneme classification, word detection, segment identification, so these sorts of things. So that's sort of the state of the field. People have been trying to build a foundation with simpler tasks and building up to full brain-to-text. And it's kind of mirroring the history of speech recognition, where people work on phoneme classification and eventually worked up to what we have today, which is widespread adoption of home assistants and that kind of thing. But it took a long time for speech. So how do you advance non-invasive brain-to-text? So here's the paper. Here's the model, and I'll point out some of the parts that are interesting. So we're building on a recent word classification model by Descoli et al., where they were just predicting classifying which word, of a subset of words. So out of 250 words, which word was it? So we're building on their model. And we make 3 contributions. The first one is maybe not going to be surprising. We scaled up the data pretty substantially. And so you can see this is in the model where we were showing different styles of scanners going into the network. Then we used rescoring. So if you have a model that can predict from some brain data which word it is, you can chain that together in time and use tricks from speech recognition. And the trick we use is called rescoring. So if you remember at the beginning, we had that matrix of time and probability over different letters. Here we're doing probability over different words. And we're finding a path through that. And we're using, separate to that, an external large language model. So basically, at every time point, you have a probability distribution from your brain model. But you can also ask your language model, how likely is this output? And by checking with your language model, you can improve the performance of the model. So that's called rescoring. And finally, we used only 250 word classifier as the base part of the model. Obviously, that's going to give you a lot of OOV, which are out of vocabulary items. So any word that's not in the top 250 is just labeled out of vocabulary. And we used an infilling approach, where we basically just gave in one version, gave the output of the model to Claude, to a large language chatbot, and asked it to guess what word is missing. And that makes significant contributions. So those 3 things together are basically the secret sauce here. Why do we limit the vocabulary size? This plot is from the Descoli paper. So they're showing on the x-axis from left to right, as you scale up the number of words you're trying to predict, so from like 1 to 250 to thousands, that the y-axis, the top 10 accuracy goes down. So basically, as you're trying to predict more words, your accuracy goes down. We find the same thing in our data. So this is showing in 2 cases. So the blue is where we're always trying to predict the top 50 words using top 10 accuracy, and the orange is we're trying to predict all the words. So if we scale up to thousands of words, we're trying to predict thousands of words. And you can see that's harder. So the orange goes further down as you scale up. And this kind of sweet spot of 250, this is where it sits in these 2 plots. So it's You could do better if you had fewer words, but actually 250 is not a large number of words. It's kind of maybe the sweet spot at the moment that we've been working on. Looking back at the Discoli paper, which is actually called Decoding Individual Words from Non-Invasive Brain Recordings across 723 participants. Very impressive. But they don't pool the data. So like I said, they've basically trained their model multiple times. So for each data set, they have a result. They don't have one result that combines all the data sets. So you can see that here in their results. They're showing results per data set. But we can scale across data sets because we've learned how. So we took three of these data sets that they're working on here, plus liver brain. And then here we did a study of how do we combine the different data sets. So let me briefly explain to you what this is showing. You're seeing across the same data sets, so they're called Broderick, Williams, Armeni, and liver brain. Going from left to right, and again from top to bottom, Broderick, Williams, Armeni, liver brain. So across the diagonal, which goes from the top left to the bottom right, we're just seeing how well can we predict words in that one data set. So that's kind of our measure of how good is the data set. And then the off diagonals are showing you when you combine pairs of data sets, how well do you perform. So some pairs of data sets you do worse on, and those are the ones in pink. And some pairs of data sets you do better on, and those are the green. So we're seeing that some data pairs better with other data. And then we exploited that to show that if you start with one data set, add the best data set, and then the second best data set, you can show that you get continued improvements. And is that right? Good, yeah. Just catching Tohan's eye there. Yeah, so this is how we've learned to scale up our data sets. So you have to be careful which data sets and in what order you put them together. The infilling, just to mention, we tried a number of methods. So this is to address the problem of vocabulary size. And this is the one approach that I mentioned before, where we're just giving Claude basically this prompt. I'll read it so it's not ambiguous. So the prompt is saying, and we're telling it this is a speech recognition model, even though it's actually a brain-to-text model. But we assumed that maybe Claude would be more familiar with speech recognition. So we say, I have a noisy speech recognition system which predicts 64 words at a time. I'm going to give you its predictions in an ordered list. UNK, unknown, this is out of vocabulary token, indicates that the target word for that position is out of vocabulary. I want you to fill in any out of vocabulary positions with words that you think fit well in the sequence. Do not replace anything that is not out of vocabulary. Your output should be formatted in a Python dictionary, mapping 64 positions, 0 index to words, preserving the system's predictions, and replacing any out of vocabulary with your suggestions. Do not output anything else. So if you guys have played with large language models, you have to tell it, don't flatter me. Oh, what a great question. Just give me the output. And so here we then give it an output example, and then we say predictions from the speech recognition system are, and this is now the list of things coming out of our model, and then the answer at the bottom is then its prediction of what the words should be. So here it's taking things that you can see, we've given it a number of 64 different words, so it goes from the, unk, sat, on, et cetera, built. And so then it replaces that unknown with cat. So the output is the cat sat on the. So in this context, it thinks cat. So here's how you go from a model that only has an internal vocabulary of maybe 64, and then it can be expanded to basically all the vocabulary that you want. These are results. I'll just point out a few things. So this is using an infilling method inside of the beam search. This is the one we just looked at, the IC fill. This is maybe the most important thing. So here we're showing our result against all prior literature across a bunch of different metrics. So on the y-axis, we have the word error rate, the character error rate, three metrics from machine translation, so blue, rouge, meteor, and then the BERT score. And basically, in the rank, higher is better. And our model, which is in the top, does better on all of the metrics than any prior model, basically. And you can look at distributions of results. So word error rate is in the middle, and we're getting a mean word error rate of 90 and the best word error rate of 86. So if you talk to speech recognition people, they'll be like, well, that's not very good. But we're very excited about this. It's effectively the first time that this problem has been significantly moved out of chance. And if anyone does machine learning, you know that there's often two parts to any problem. The first is reaching around, grasping in the dark, trying to get anything to work. You try. You have no signal. You don't know what you're doing, but you try stuff and you have faith. Or your supervisor tells you, this is part of the process. Then you get a signal at some point, hurrah, and you can optimize it. And machine learners love nothing less than to optimize an objective. So this means basically we're in the optimize an objective phase of this problem. And that's basically why we're excited. Cool. So just to finish up, I'll talk very briefly about some thoughts on outlooks and opportunities. Here are some of the things the team is working on at the moment. To bring out some themes, there's even more data to come, so we're not stopping at LiverBrain, we're going above and beyond. We're going to release our data as usual, keep it high quality, make it easy to use. We're also expanding into high quality inner speech. So we were showing you data where people were listening to audiobooks. So this is often a simpler task that people have used in brain to text to get things going. But we really want to be working on imagined speech or inner speech. So we already have some data sets that show we're getting signals. So we're basically trying to transition into inner speech data. So that will be a big push. So we have a few data sets already staged for release. But yeah, I expect these will come out this year. And also we're collecting data in other modalities like EEG, MRI, FNIRS. We're interested in foundational neuroscience, so we want to understand what is the nature of inner speech. I mean, it's surprising to me as a scientist that actually we know so little about inner speech, given how ubiquitous it is. And I had to get over this, and I imagine this must be true for others. It's really easy to argue from analogy that whatever my experience is, everyone else must be the same. And if you do the simple exercise of asking people, you find out that no. We had one person in the group for a while who claimed he had no inner speech. And when he said that, like, things made so much sense because he will talk to you. And while he's talking to you, he sometimes is amused and laughs because he's never heard what he's saying either. He doesn't know what he's saying until he says it. So maybe that's what it's like to have no inner speech. We want to know how this is related to other types of speech, so speaking out loud and hearing. And we want to know about individual variation. And that's partly because we just want to know about it as foundational science, but also because we want to be able to generalize models to patients, to all patients. We're trying to use more compute, so we're looking at obviously large language models and foundation models. And one of the problems with foundation models of speech is how do you tokenize or chunk your data? So we're looking at that and other kinds of problems. We're also looking at various kinds of generative models and multimodal models. We also want to be really good humans. So the reason that we do this, obviously, is because it could make a profound difference to some people's lives. So this picture here, I don't know if you can read it, but this is from a recent study, and he's using implanted electrodes and saying freely whatever he wants to say by thinking it. And what he says is, I hope that we are very close to the time when everyone who is in a position like me has the same option to have this device. I mean, my favorite thing, I didn't find the video in time, but the same patient, the first time they hooked this up for him, they had to register the experiment as a failure. They got no useful output because he was crying with just relief. So that's what we do this for. I mean, at the end of the day, it's not just academic. We want to get this to people. We want to change lives. At the same time, we know that there are potential risks. So how do we minimize the risks of bringing this technology into the world? And I think this is a good case study for all people, especially maybe students who are thinking of getting into transformative technology. How do you maximize the good and minimize the bad? One way to do it is to do it in academia and do it openly, which is what we're doing, trying to make this a crowdsourced effort and to be transparent and to bring other people into the conversation. We are also simultaneously working on a spin-out, and that's raised a number of interesting questions. One of which is thinking about how to make these things secure. And I have a lot to learn in this space, but one thing I've been very inspired by are things like Signal, where they have algorithmic security. So they have a protocol which is public. So it's not just trust me at my word that we're going to keep this private. It's that the actual underlying mathematics and engineering has no way of sort of keeping your personal data, let's say. So no data is sent anywhere. Everything is on device and doesn't physically go anywhere. Never capture data. So I've also been inspired by the recent problems at 23andMe, where maybe they had the best intentions, but they've reached a position where they're no longer in control of all of these people's data. So this is also talking about maybe creating an architecture and expectations amongst users. So if this were created, say, by a company that built sort of like ads into it from the beginning and always took your data, and that was just the way things were, you might just think, well, that's how this technology has to be. But we want to create, from the beginning, the expectation that, no, that's not how it's supposed to be. You have an alternative, and that should hopefully put pressure. Not to say that will solve all the problems. We want to collaborate. If you're ethicists or if you have other ideas, we need help. It's hard enough to do the science. Figuring out how to do policy and ethics is, maybe harder. And we have sourced some funding, actually. So we will have a workshop, hopefully here in Jesus in the next few years, where we bring together all the leading labs that are pushing this research and ethicists and policymakers to think about what are the levers we can pull. I mean, I assume there's a window in which scientists have some kind of control over the technology, and that window is probably pretty small. So maybe we should do that sooner than later. But do we need to do public engagement? Do we need to actually try and change policy? What are the problems we're worried about? Get into a room and kind of get on the same page as much as possible. So that's the hope. If you have other ideas of how to do this, please let me know, because we want to maximize the good. So this is the advertisement part of the presentation. If you are a master's student doing machine learning, we're taking 1 to 2 over the summer. If you're a DPhil student, we tend to take 1 to 2 per year. We're looking for a postdoc to work on decoding arm movement for robot applications. This isn't really solid yet, but there's a good chance we'll be looking for a postdoc to work on NLP for both low resource languages and bridging that into BCIs, and also automatic speech recognition. And yeah, ethicists, you could be master's level, DPhil, PI, whatever, basically I'd like to embed someone in the group, possibly, but we'll see. Anyway, those are the kinds of things we're looking for. And for the spin out, we're also looking for people who might want to acquire data. The optimal candidate might be someone who just finished a recent master's degree but wants to stick around and knows how EEG works, and also AI researchers, software engineers. So these are all the papers we cited from the group. Thank you very much.